Alright, next on the Feynman diagram fun, we're going to look at beta-negative decay using a Feynman diagram. And we're going to look at this from the perspective of particles. We'll talk about quarks a little bit later. So in a beta-negative decay, the main gist of what's going on is we're going to have a neutron. It's going to decay into a proton, and an electron, and an antineutrino. What we want to do is we want to actually sketch this out. Now, I'm going to show this, and again, if you don't completely understand how we're drawing this, don't worry too much about it for now. We're just trying to show you the highlights of a Feynman diagram, because a little bit later I'm going to show you what a typical question is going to be on an IB exam. You're most likely not going to get examine this beta-negative decay from a Feynman diagram and start from scratch. They're going to help you out a lot from it. We're just using this to kind of show you the basis or the theory. So the first thing is we want to just talk about the neutron. So I'm going to just sketch a neutron here. It's doing its happy little thing. It's a standard particle. It's not an antiparticle, so we don't have to draw the arrow against time. So I'm going to label that. And now eventually this lovely little neutron, it's going to decay into a proton. But that's not the end of the story. So this is now decayed into a proton, but we also have to deal with the electron and the antineutrino. All three of these have to branch out from the same point. So this neutron is being converted into a proton here. This point where the conversion happens, this is a special point here. This is what we refer to as the interaction vertex. So the interaction vertex is really special. With the interaction vertex, we want to ensure that all the conservation laws of the part are respected with the particles going in versus the particles going out. So we have a neutron that's decaying into a proton. We also know that this is going to decay into an electron and an antineutrino, but it's not going to decay into that directly. We also know from beta decay, whether it's beta positive or negative, this is going to be the weak nuclear force involved. What that means is we're using some type of boson. The boson is going to be the carrier of that weak nuclear force. So when that neutron converts into a proton, at the same time, we have to deal with that weak nuclear force. And the weak nuclear force is going to be carried by this boson. What type of boson? Like I said, we'll talk about it later. So we're just going to sketch this boson with a dashed line. Now, at this interaction vertex, we have a neutron coming in, we have a proton and some type of boson going out. So at the first interaction vertex, so we have a neutron going in, we have a proton and a boson going out. What this means is that the conservation laws have to be respected at this interaction vertex. The conservation laws that we are going to be looking at in Feynman diagrams, it's usually going to be the conservation of the baryon number and the conservation of charge. What that means is that the conservation of the baryon number of the neutron, I'm just tripping over my words here. What we're trying to say here is that the baryon number of the neutron, it has to equal to the total baryon number of the proton plus this boson. And we also have to respect charge. So the charge of the neutron, that has to equal the total charge of this proton plus this boson. So first of all, let's look at the neutron. Let's look at the charge laws here, because we want to take a look at that more in depth. So a neutron is a baryon. It's composed of 3 quarks. It's composed of an up quark and 2 down quarks. So this is going to have a baryon number of 1. And a neutron, we also know it's not charged. So we're going to say for charge, it's going to be 0. So this is what's going into the first interaction vertex. So this is going into I'll call the interaction vertex IV. So going into that interaction vertex is going to be a baryon number of 1 and a charge of 0. Coming out of this interaction vertex, we must have the same rules. We must have a baryon number of 1 and a charge of 0. We can deduce some things about the proton because we know things about the proton. A proton is also a baryon. So it is going to have a baryon number of 1. For relative charge, we know that the charge on an electron is 1. So at this first interaction vertex, we need to deduce some information about this boson. So we need to know information about it, whatever boson that this happens to be. So in terms of the first interaction vertex, I have a baryon number of 1 going in, and then I have a baryon number of 1 with the proton plus this unknown baryon number of this boson. Well, 1 equals 1 plus, well, the unknown here is going to be 0. So this boson is going to have a baryon number of 0. For charge, we have a charge of 0 coming in with the neutron. We have a charge of 1 with the proton. So we need to figure out what is the charge of this boson. Well, in order to conserve charge, this boson has to have a relative charge of -1. And the charge of the boson is going to tell you what type of boson we have. We have the options of a W plus, a W minus, and a Z0. So W plus is if the relative charge is +1, W minus is the charge if the charge is -1, and Z0 is if the charge is 0. Given that we have a charge of -1, this tells us that we have a W minus boson. So what we're saying in this case is that in a beta negative decay, this neutron is going to decay into a proton and then a W negative boson. But that's not the end of the story. In this decay, we also have to deal with the electron and the antineutrino. Well, they themselves are going to decay from this W minus boson. So I'm going to sketch this down a little bit further, just to give myself some space. So then we're going to have a second interaction vertex here, because then this W minus boson, it's going to decay into our electron and our antineutrino. So we can sketch those out here. So I'll sketch my electron here. So there's my electron, and then I'll sketch my antineutrino here. Now again, because it's an antiparticle, I want my arrow to go against the flow of time. So this is my antineutrino. At the second interaction vertex, we still have to conserve baryon number and charge. So I'm going to sketch for the second interaction vertex. So what we have here is we have a W minus boson going in, and then we have an electron and an antineutrino coming out of this. So we already know going into this interaction vertex, we have a boson number of 0, or sorry, a baryon number of 0 and a charge of -1. Well, for the electron, we know that the electron has a baryon number of 0. Being a lepton, a fundamental particle, it's not going to be made of quarks, so it can't have a baryon number. And we know the relative charge of the electron is -1. For the antineutrino, we know that it's a lepton, so it's going to have a baryon number of 0, and the antineutrino does not have a charge. So are the conservation laws respected? Is the baryon number of the W minus boson, is that equal to the total baryon number of the electron plus the antineutrino? Well, 0 definitely equals 0 plus 0. So at this interaction vertex, we've conserved the baryon number. Is charge conserved? Well, we have -1 coming in, and then after the interaction vertex, we have -1 from the electron, 0 from the antineutrino. So we do have conservation of charge. So we've conserved all of our conservation laws here. So that's good. So this is meant to show us a sketch of a beta negative decay. As I said, you would not be expected to know how to sketch this from scratch. That's a bit of a high demand for a high school student. This is just meant to show you like what we mean by interaction vertex and how we look at the conservation laws at that interaction vertex. We're going to do one more example like this in the next video, and then after that I will show you what is a more typical question you would see on an IB exam. So if this is scary, don't worry. Hopefully we'll take the fear factor away soon.